Hello everyone. In this particular session related to material science module 2, so we are going to study different concepts wherein the combination of materials are taken into account. So we are generally adopted to few of the definitions like alloy, composite material as such. So whenever we have two or more materials, we are going to define a specific pattern for alloy as well as for composite materials. Whereas here, considering the concept of alloy, we are going to consider the combination of various materials and we are going to understand the behavior of material at certain parameters under certain conditions of combination. So in such case, we have the specific topic to be considered in the study, the first one being binary phase diagram. So in this particular class, we are going to study the concept of binary phase diagram, Gibbs phase rule and eutectic systems. So these are related to the combination of components. So what do you mean by binary phase diagram? Before understanding the concept of binary phase diagram, let us define the term called as phase diagram. A phase diagram is the graphical representation of physical states of substances under different conditions of temperature and pressure. So whenever we go with the combination of materials here, we always target something called as temperature and pressure. This particular combination, that is temperature and pressure, results in variation in the adaptation of materials or mixing up of materials leading to a particular material that serves the purpose of particular application. So here the phase diagram represents it is a graphical representation that represents the physical states of substances under different condition of temperature and pressure. So with respect to a particular temperature, what will be the condition of material in the combination with the other material? So here what happens, when we take binary phase diagram into context for the same graphical representation as defined in the phase diagram, the number of components will be minimum 2. When we have two components in the limit and we are going to assess the physical state of those two components at various parameters called as temperature and pressure, we are going to define the term, we are going to define the entire phase as the binary phase and the graphical representation is taken into account as binary phase diagram. So here what happens, in order to go with the equilibrium condition, we always try to retain the pressure as 1 atmospheric pressure and constant throughout the combination of material. So in case of binary phase diagram, this is to be noted that 1 atmospheric pressure is the constant pressure taken into account. So let us understand the graphical representation of the binary phase diagram. So here along y-axis we are going to take the temperature in degrees Celsius. Along x-axis we are going to take the composition of two materials. Here you can observe here we have represented the nickel and copper combination here. So nickel is represented along the blue color line, whereas the combination of copper is represented along the pink color line. So here, in this particular graphical representation, along the x-axis, we are going to find the combination of material, that is nickel and copper. So you can observe the x-axis here, 0 to 100 and simultaneously 0 to 100 from the right side. Means to say that if we have 0% of copper in the mixture, then it consists of 100% of nickel. Similarly, if we take 60% of copper, then we will be having 40% of nickel. So this is the combination of the two materials. Here in this particular diagram, you can observe here, A is the melting temperature of nickel. So I have quoted A along the same color chalk for the reference here. So A is the melting temperature of nickel, whereas B is the melting temperature of copper. So here what happens, when we have the combination of two materials, we are going to heat the material so that the material gets merged with one another in the liquid state and then we solidify. That is where the process of solidification and solid solution comes into picture. So here what happens, these are the two varied temperatures at which the melting up of the respective material take place. So here A is the melting temperature of nickel, whereas B is the melting temperature of copper. So in order to go with the mixture of these two, the line joining A to B above the liquid and solid solution is called as liquidus line, whereas the line or the curve that represents from A to B below this liquid and solid solution phase is called as solidus. Means to say that when we heat the material A and when we heat the material copper and nickel to a particular temperature, say A and B here, what happens is these two metals mix together in liquid plus solid solution that is represented in between these two lines. So when the materials are completely melted, that is when the materials are completely available in the liquid state, that is where it is represented above the liquidus line. Above this liquidus line, we have both the materials in liquid state. Below this particular line represents solidus line, and below this line both the materials will be available in the solid form. So this is where the graphical representation of binary phase diagram comes into picture. Now let us take up the next major parameter here, that is Gibbs phase rule. What is this Gibbs phase rule? So it is a rule named based on Gibbs which relates the number of components and the number of degrees of freedom of that particular components in a system kept at equilibrium. So means to say that when we have two materials, when we have these materials to change its phase from liquid to solid and solid to liquid, okay, at an equilibrium condition in a system, how do these particular materials as well as the combinations is going to be addressed? That is where the relation is being defined under the heading Gibbs phase rule. So it is represented using the equation P plus F is equal to C plus 2. What does these particular value represents? P represents the number of phases in which the components is being considered. So here if you take in this particular phase itself, so the nickel is available both in solid and liquid state. So that is where the number of phases is going to be taken into account. Next comes F. F is the degrees of freedom. So in what particular extent the material do get the conversion from one state to another state. Next comes C, that is the number of components at equilibrium. So here we have two components in this particular diagram. So we can take C is equal to 2. Here the number 2 represents two variables, that is temperature and pressure. So whenever we go with the combination of material, the major variables that attract the material combination is the temperature at which the material is considered and the pressure in which the material is being considered for its mixing. So here what happens, the 2 represents two variables, temperature and pressure. But as we have defined in the binary phase diagram, at equilibrium condition, the pressure is always kept as 1 atmospheric pressure and it is constant. Since it is constant, now we are going to replace the two variables by one variable, that is temperature. Okay, we are going to retain the temperature as one variable, but the pressure remain constant. Hence what happens is the same Gibbs phase rule under the equilibrium condition, since the pressure is kept constant, P plus F is equal to C plus 2 turns out to be P plus F is equal to C plus 1. Remember this, one is not atmospheric pressure, one is one variable, that is temperature, which is accounting for the mixture of two components. So this 2 is turned into 1 basically due to the consideration of atmospheric pressure 1 is constant in the equilibrium condition. So this is about the binary phase diagrams and Gibbs phase rule. Now let us take up eutectic systems. Let us start the study on eutectic systems. How do you define eutectic system? So it is defined as a system where two components which are completely soluble in liquid state are either will be taken into two cases. Means to say that when we have a combination of two metals, say for example metal A and metal B. So let us define A as A and B are the pure metals here. So when we mix these two metals and when we heat it in the liquid state, they are completely soluble. What happens when it comes into solid state? Because at the end of the day, we are going to get a solid product out of the mixture of A and B here. So in this case, in case of eutectic system, we are going to define that condition in solid state in two phases. Point number 1, see, you have to read like this. Two components are completely soluble in liquid state, are either completely insoluble in solid state, case number 1. Case number 2, the same two components which are completely soluble in liquid states are partially soluble in solid state. Means to say that when they merge together to form a solid solution, they will be of two cases. One is they will be completely insoluble in solid state, or it will be partially soluble in solid state, whereas in case of its liquid state, both the metals will be completely soluble. So we can represent the same condition A like this. So in liquid case, both pure metal A and B will be completely soluble. So whereas in case of partially soluble in solid state, it will be like this, where alpha and beta are taken as alpha is A rich solid solution, beta is taken as B rich solid solution. So in case of the second condition here, where is completely soluble in liquid state, partially soluble in solid state, we can see like this. In liquid state, A and B will be mixing together, whereas in case of solid state, means to say that when you are going with cooling those metals to form solidified product, at that particular point of time when you cool it, since it is partially soluble, you will get alpha and beta, which are rich mixtures of A and B respectively. Upon heating, that is in the liquid state, wherein the same alpha beta will be completely merged in the liquid state, hence A plus B is represented as liquid here. Case number 1, that is completely insoluble in solid state, means to say that when two metals, that is A and B, are heated in the liquid state, they will be completely soluble, whereas when you cool it, when you make it into solid product, what happens? The same mixed pure metal A and B will become completely insoluble, that is A plus B remains as it is. So these are the two cases wherein eutectic systems are defined. So let us take the first case now, that is two metals completely soluble in liquid state and completely insoluble in solid state. So let us take the pure metal A and pure metal B, wherein the combination is represented along the x-axis, while the temperature is represented along the y-axis. So here you can refer this particular drawing, even the notes will be shared. A very clear picture of understanding how to read this particular drawing is essential, rather than by hearting or writing the entire script. So let me teach you how to read this particular drawing first. See, along the x-axis I have taken two metals, one is A, another one is B. A is 100% towards the left, whereas B is 100% towards the right. Means to say that along the y-axis, whatever we represent on the left side, it is completely related to the pure metal A, whereas whatever the temperature we represent on the right hand side, it is completely related to pure metal B. This is the first point of understanding. Followed by, here we are supposed to define again the phase transformation or consideration of metals in different phases. So as we defined in the binary phase diagram, above the liquidus line, both the metals will be in liquid state. Below the solidus line, both the metals will be in the solid state. So you can observe here, these are the lines, that is from TA to M. M to TB is the liquidus line. We have represented the same here for reference. TA to M, M to TB is liquidus line. So above which both the metals will be in liquid condition. Means to say that in eutectic system, as per the definition, both the metals A and B will be completely soluble in the liquid state. Means to say that above the liquidus line, both the metals will be completely soluble. Similarly, TA to TE, TE to M, M to TE, TE to TB is the solidus line, that is represented TA to TE, TE to M, M to TE and TE to TB and solidus. See here, I have already defined whatever we represent towards the left is related to pure metal A and towards right it is pure metal B. Hence, TE is represented on both the sides and we consider TE for the representation of solidus line twice, that is TE when it comes to pure metal A, similarly TE, that is eutectic temperature, considered with respect to pure metal B here. So the line from joining from TA to TE, M, TE and TB, that is a blue color line, represents solidus line. Means to say that below the solidus line, both the material will be in its solid condition or solid phase. So now let us take up the understanding of eutectic composition. So here TE represents eutectic temperature, whereas 1 represents eutectic composition. Why we take 1 as the eutectic combination is that, as per the definition, both the metals should be completely soluble in the liquid state, but when it comes to solid state, where is when there is an initiation or solidification is being considered, both the metals become insoluble. Hence, this is a point wherein the pure metal A and pure metal B, okay, is solidifying at this particular point. So the point of contact wherein both the pure metals A and B is solidified or solidifying at that particular point is called as M, and that is represented as the eutectic point. And the composition of pure metal A and pure metal B that is leading to the eutectic point, hence that particular composition called as eutectic composition. Here in this particular representation, it is 70% of B and 30% of A. You can refer the figure. So it is 30% of A and 70% of B. That is the combination wherein which both the pure metals are combining together or solidifying together while it is completely insoluble in its solid state. Hence, that is the composition which is to be referred as eutectic composition, the point wherein which both the the pure metals meet together to initiate or to completely solidify. That particular point is called as eutectic point. So now let us take the this is how we are supposed to understand this particular consideration of composition. So here you can refer at this particular combination, we have represented A plus B within the bracket, which represents it is completely insoluble in the solid state. So that is where we have taken A plus B is equal to eutectic structure, where A and B are pure metals. So let us start considering the solidification of pure metal A and pure metal B to form a particular product satisfying the condition of first case in case of eutectic system. So here, for the purpose of understanding, along with the eutectic composition, we can take any combination for the purpose of understanding. So we have taken the composition 2 here that represents 20% of B and 80% of A. Similarly, 90% of B and 10% of A is considered as the third composition. See, this second and third composition is not stagnant. You can take wherever you want to understand or assess the behavior of composition. So for the purpose of ease of understanding, I have taken the composition 2 as 20% of B and 80% of A. So let us now start with respect to this particular position, how the solidification is being initiated. So here TA represents the melting temperature of pure metal A, whereas TB represents melting temperature of pure metal B. Let us concentrate on the composition 2 now. This composition 2 is completely relevant to the rich mixture of A material here rather than B, because percentage of A is identified to be 80% while percentage of B is considered to be 20%. So this is our consideration. It is not stationary or stagnant. So in this particular condition, since it is completely consideration with the A material in the rich composition, so we are going to assess the condition of A metal first. So with respect to the second composition, the point of intersection wherein that line drawn from 80-20 composition to reach the liquidus line, we have taken it as T1 temperature, T1 degree Celsius. What do this T1 degree Celsius represents? T1 degree Celsius represents the initiation of solidification. As we all remember, it is the process of heating both the metals to a liquid stage, and then once you start solidifying, both the materials converge together to form a solid product. Okay, so what happens? Both the metals are in its melting condition at TA and TB respectively. Now you are reducing the temperature, that is, you are taking off the heat which is supplied to the material to transform the material from solid to liquid. So once you have removed the heat, what happens? The temperature should reduce. So with respect to composition 2, what we have taken, that states the solidification process is in progress, means to say that TA to T1 it is reduction in the temperature, means to say that from liquid to solid the solidification process is in progress. Similarly, We will take one more composition here which we have not mentioned here, say okay, that is 40% of B to 60% of A. Here also again the percentage of A is more now, so we can again rely the entire thing on pure metal A. So for the same composition, if you draw a vertical line that meets the liquidus line, what does it represent? It again represents the continuation of solidification process of pure metal A. Okay. Similarly, for one more composition, that is 40% of A and 60% of B. Here it is not consideration with respect to rich mixture of A, but this is lesser percentage of consideration rather than the eutectic composition. Means to say that here see 60% of B and 40% of A is not the eutectic composition. Okay, it is before the eutectic composition. So hence what happens, if you just draw a vertical to the line, that is liquidus line, the temperature is considered to be T3 degrees Celsius, which is giving us the information that the solidification process is almost over. That is, the temperature is still more reducing. Okay, at a particular composition M, what happens? It is a point wherein the TB, that is the temperature or melting temperature of the pure metal B, tends to lean or reduce to form a solid solution. So this is consideration of T1, T2 and T3. Now let us go with T4 and T5, which is completely relevant to the pure metal B here. You can observe the composition here. I have taken T4. So T4 is the temperature corresponding to what? Corresponding to the composition which we have considered for the assessment. The composition is 90% of B and 10% of A. Here again what is happening here? It is the addition of the rich mixture of pure metal B here which is been identified. Hence what happens? So TB being the melting temperature of the pure metal B. So T4 is the corresponding temperature to the composition what we have taken to assess the phase of the entire combination. So what happened? T4. What do T4 represent? T4 represents the solidification of pure metal B here. Okay. Still more, I'll have another option here. I can take one more combination, that is 80% of B, 20% of A here. Again, drawing a vertical line to meet the liquidus line, the corresponding temperature will be taken as T5 degrees Celsius. What do this T5 degrees Celsius representing? It is representing the conversion of the liquid state of pure metal B into solid state. When these two liquidus line of pure metal A and pure metal B meet at a particular point wherein the complete solidification happens, that is a point which is considered as eutectic point, that is represented using the capital letter M. So this is where the eutectic system of first condition, that is, remember, completely soluble in liquid state. Both the metals are heated to melting temperature. In the liquid state, both the metals are mixed. Whereas once we consider the solidification process, at a particular point, both the metals will be completely insoluble. They are not going to merge together, and that is a point wherein it is considered to be the eutectic point, that is capital letter M here. So here, addition to that, we have other representation, that is TR, which represents the room temperature, which is the minimum temperature wherein the material will be kept under the observation. So along with that, A plus of A plus B means to say that, as I said, there is rich content of A here in the entire solid solution, that is A plus of A plus B, whereas here it is the percentage of B is rich here. So B plus of A plus B means to say that rich mixture of B plus the eutectic composition. So this is the first type, or the understanding of first type of eutectic system. Let us take the second condition, that is two metals completely soluble in liquid state but partially soluble in solid state. So you can just refer this particular representation here. So here what happens, instead of taking pure metal A and pure metal B, we have considered the combination of copper and silver here. So to the left it is the maximum percentage of copper, to the right it is the maximum percentage of silver. So in this mixture we have to analyze such that there is a partial solubility. See, all the metals will not satisfy this particular condition. There will be particular combination of material that comes under the second case, that is completely soluble in liquid state, partially soluble in solid state. Whereas in few cases it satisfies the first condition of eutectic system. So in this particular diagram, we have bit tedious representation of the lines that represents the partial solubility of the metals in solid state. So here you can observe, as it is said, so TA is the melting temperature of copper, that is 1083 degree Celsius, whereas TB is the melting temperature of silver, it is 961 degree Celsius, whereas the eutectic temperature is 780 degrees Celsius for this particular combination. See here we have directly quoted the number because we have directly taking the combination of copper and silver here. So to represent again, it is again to understand the same diagram here. So the line that represents from A, C and E here is the liquidus line, whereas the line representing from A, B, C, D, E is the solidus line. Here, since we have partial solubility, we are going to get two additional representation, that is called as solvus line, that is from B to F here and D to G here. So B to F and D to G is the solvus line representation. So let us now start the consideration of mixing up of these two materials such that it satisfies the partial solubility in the solid state. So say we have taken copper and silver mixture. So we have heated both the materials. So when heated at 1083 degrees Celsius, the copper converts completely into liquid state, whereas at 961 degrees Celsius, the silver completely converts into liquid state. So this line represents the liquidus line above which the material will be completely soluble in the liquid state. So the line that represents here is the solidus line below which the entire material combination will be solid in its structure. So here you have to observe the solid structure will be represented beneath the solvus line, not for the entire representation of composition. Okay. So now the point at which the complete solubility happens here, whereas in case of first type we had represented using the letter M here. So now for the purpose of understanding, we can take any letters for representation. Here we have considered the point C, wherein both the metals, that is copper and silver, under solidification process come and meet at a particular point, and that particular point satisfies the eutectic point, and the composition of that particular the eutectic point is 72% of silver and 28% of copper. You can observe with the composition here. Along x-axis it is the composition, along y-axis it is the temperature. So the composition here, alpha plus beta, is written as considered in the representation of second case of phase diagram here. So here, similarly, we can take multiple number of compositions to assess the behavior. Here, mandatorily we have to take two composition that results in the partial solubility of two metals. So that composition goes with 3 and composition 4 here, wherein it lies in the range wherein partial solubility is considered. So alpha and beta, as we have defined here, alpha is the rich mixture of A material. So here the material A is copper, which is taken towards the left side, and here beta is the rich mixture of silver material, since silver is taken towards the right for the representation. So here second composition is taken just for the assessment of the solidification of both the composition here. So here you have to observe carefully, since the first composition is the eutectic composition, the second composition is considered for the purpose of understanding. The corresponding temperature is taken as T1. Okay. Similarly, for third composition of assessment, the corresponding temperature with respect to liquidus line is taken as T2. So you should not consider like T1 should be at the top, T2 should be at bottom, not as such. It is the sequence in which we considered for the assessment. So T1 is related to the second composition what we have considered for the assessment. So as per the second composition, say 30% of silver, 70% of copper, what we get is the initiation of solidification process in composition with the rich mixture of that is copper or the metal A of consideration here. So going with the composition 3, which represents the partial solubility, we have alpha here. So with respect to the composition, say for example, we have taken say around 5% of silver and 95% of copper for the assessment here. So with 5% and 95% of composition, so what is happening? The corresponding temperature leads to T2 degree Celsius. The T2 degree Celsius results in the solidification of the copper material, that is material A in consideration here is in progress, or it is initiated. So what happens at that particular composition? Around 8% of composition, this 8 is the composition of silver, whereas towards left 9% is the composition of copper. So that is where you are supposed to put your interest on. So where actually the partial solubility comes into picture. So when the composition of copper and silver goes with 8% of silver with 92% of copper, there leads a particular point below which the rich mixture of material A or the rich mixture of copper is being considered. Similarly, for around 9% of copper to that of 91% of silver, you are going to get the partial solubility of B, that is material is silver here, silver mix, silver rich solution in the consideration. So here we have not represented the room temperature as in case of first condition, because there the temperature was focused from 0 degree itself, whereas in this particular representation we have represented from 400 degree Celsius as such. So it is 400 degrees Celsius and above. Since with the representation itself goes with 400 and above, we are considering no presence of room temperature here. So this is about the representation of partial solubility of the liquid metals in solid state, whereas completely soluble in the liquid state. Okay, so in solid state it is partially soluble, whereas in liquid state it is completely soluble. So alpha and beta represents, alpha represents the rich mixture of copper, whereas beta represents rich mixture of silver. So the main concept of understanding this diagram is to assess the behavior of various composition. So here 1, 2, 3 and 4 are only the point of concentration or wherein we are going to check, whereas 1 is always the constant number which represents the eutectic composition only. See here it is not 70-30, it is the eutectic, exact eutectic composition, it is 72% of silver, 28% of copper. Okay, so similarly for alpha and beta it is exactly the percentage of rich mixture of partial solubility in solid state is attained when copper is 92% and silver is only 8%, whereas in case of partial solubility of B, that is rich mixture of silver is achieved when 91% of silver is seen with 9% of copper. Okay, so this is the representation of partial solubility of material in its solid state with completely soluble in its liquid state. Thank you.